All right, everyone, congratulations. We've made it to the last video here on our Chapter 9 practice test. This is going to be our word problem type questions, and we're going to work in a lot of the review things from Chapter 8 here. So for 21, it says that each cross-section of a solid infinite horn bound by the x-axis and above by y equals e to the x, cut by a plane perpendicular to the x-axis for x between negative infinity and natural log of 2, is a circular disk with one diameter reaching from the x-axis to the curve y equals e to the x. Find the volume of the solid. We have cross sections perpendicular to the x-axis, and we're going to draw those in here to our curve. This is the natural log of x curve. That point that you see there, that is the natural log of 2, comma 2. Now if we draw in the ovals here, hopefully you can see kind of what this shape looks like. Kind of reminds me of an old-timey ear horn, if you know what those look like. Maybe something like that. So okay, it's not so hard to imagine. The cross sections perpendicular to the x-axis are circles. So what we want to do is we want to do a y1 minus y2. So I'm going to save this one circle over here, and I'm going to get rid of the rest of them. And so this segment that I've just drawn right here, this represents the diameter of the circle. And the length of this is going to be the y-coordinate on top minus the y-coordinate on the bottom. So what is the y-coordinate on top? Students who don't have a lot of experience here will say, well, you got it from this point right here, so isn't the y-coordinate 2? And that's where I say no, because this needs to stand for any of the diameters across this horn. So it's not always equal to 2. That y top is actually on the curve of e to the x. And if y is equal to e to the x, then the y-coordinate on the top curve is e to the x. Likewise, on the bottom here, this was at the x-axis. Now this time, the y-coordinate is always going to be on the x-axis. So the y-bottom is going to be equal to 0. So the length of this is going to be e to the x. Now if I'm following my own game plan, which is corners, length, area, and integrate, then I'm going to have to figure out the corners. I should have done that earlier. And if this is my region, then the only other corner that I forgot is that natural log of 2, 0. Remember that we're going to infinity over in the negative direction, in the x-coordinates. Now it pains me a little bit to write this, but the far corner over on the left, that's going to be at negative infinity 0, even though that's not really a coordinate. That's really bad math on my part, but I don't have a really good way of expressing that for you. So we've got the coordinates of our region. We've got the length of our region. Let's move our game plan a little bit so that we have more space to operate. Okay, the area of our region is a circle. I think you see we've just drawn circles, and over here it says a circular disk as well. So the area formula that we need is the area formula for a circle. Okay, so the area of each cross section is pi r squared, and now we've got to figure out how does the radius relate to my length over here. Well, looking back here, the length is the diameter of the circle. So the radius is going to be half of that diameter. And since the diameter is the same thing as L, the radius is 1/2 of L. So that radius is e to the x over 2. Bringing that back to my game plan, now that I know that the radius is L over 2, or e to the x over 2, I can get my area formula down to pi multiplied by 1/2 e to the x squared, which simplifies to pi over 4 e to the 2x. Be careful with that squaring. Some people don't do that correctly. I know you're not going to be one of them, though. With that area formula in place, we are now ready to integrate. the area formula is the volume formula is the integral from a to b of ax dx. Looking back at my corners, the smallest value for x is negative infinity. The largest value of x is the natural log of 2. And then my area formula is pi over 4 e to the 2x. And that should get me well on my way. I notice that we have a lower limit that's negative infinity, so we're going to replace that. Pi over 4 is constant, and the antiderivative of e to the 2x is 1/2 e to the 2x. Now we're just going to substitute our limits. Now a couple things to point out here. First of all, this e to the 2 natural log of 2, I can use properties of logs to make that into e to the natural log of 2 squared, which is just e to the natural log of 4. And then e to the natural log of 4, well, e and natural log are inverse operations, so that's just equal to 4. And then pi over 8 multiplied by 4 is just pi over 2. Well, that takes care of that. Now in the second bracket here, we have e to the 2a, and a is going to negative infinity. So think about what that means. We're saying that a is going to negative infinity. So the exponent of e is actually a positive number. Wait. A negative number. The exponent of e is a negative number, which means what we really should be looking at is 1 over e to the 2a as a goes to positive infinity. Because remember, a was going to negative infinity before. If we make it go to positive infinity, then we could just move e to the 2a to the denominator. And well, what happens there? Well, the denominator is going to grow without bound. The numerator is constant, and as we've said before, this limit is actually 0. So there you have it. The volume of that infinite region is going to be just pi over 2 minus 0. That's always kind of mind-blowing to me, because we're saying, think about what we're saying. We're saying an infinite region has an area equal to pi over 2. That's like 1.5, 1.6, 1.58. Okay, who's counting? But yeah, that's weird, right? Infinite, yet the volume is equal to 1.58. Mind-blowing. Anyways, that takes care of this problem, and this is going to be our last problem of the practice test. Again, an infinite region bound by the coordinate axis and the curve y is equal to negative natural log 2. This time we're going to revolve this around the x-axis to generate a solid. Let's find the volume of that solid. Let's start off by taking a look at what this solid looks like. Here's a little bit of the graph of y equals negative natural log of x. And we're bound by the axes, so I've cut it off over here on the x and y axes. And I know that this part right here, this is going to go all the way to infinity. So that's where my problem is here. As x approaches 0, we're going to go to infinity. We're going to get the corners here first. I'm not going to make that same mistake that I made before. That's definitely 1, 0. That's definitely 0, 0. And up over here, we're going to treat this as 0 all the way to positive infinity. So when we get my game plan, I've got my corners here, even though infinity is not really a coordinate. Okay, we are revolving this, so we know that we have cross sections that are circles. So we know the area formula is going to be pi r squared. To get the radius is going to be the distance between the axis of rotation and the outermost curve. We're revolving around the x-axis right over here. So we know that the x-axis, since it is one of the boundary curves, this is going to be, since the axis of rotation is a boundary curve of r, we know that we're going to get a disk method. So I think we've got a lot to go on here to start our game plan. Same game plan, corners, radii, or radius or radii. Actually, since this is a disk method, it's just one radius. Then what is the area formula? And then we integrate. We already have our corners. We know that that's 0, 0, 0, and infinity. Oh, that hurts. 0, infinity as a coordinate hurts. Sorry. And then 1, 0. And from that, we can deduce what our a and b is going to be. Perfect. A is 0, b is 1. Next, we're going to find our radius. Now, the radius is always going to be the distance between the axis of rotation and the curve. So we're going to draw a radius somewhere in the middle of our curve. Okay, up over here, this is y top, and this is y bottom. And the radius is going to be y top minus y bottom. Now the y-coordinate on the top is always going to be on that curve, and that curve is negative natural log of x. Y bottom is always going to be on the x-axis, and the equation of the x-axis is y equals 0. So here is my expression of the radius, negative natural log of x minus 0, which of course is just equal to the negative of the natural log of x. That's my radius. Scrolling down to the game plan, we'll go ahead and write that in. R is negative natural log of x. Since the cross sections are circles, we know the area formula is pi r squared. Remember, because it is a rotation, we don't even have to fuss with it. Every rotation creates a circular cross section. And we have the radius. The radius is negative natural log of x. So we can simplify our area formula again. And actually, we can simplify this just a little bit more, because if I square negative natural log of x, that's kind of the same thing as negative 1 squared multiplied by natural log of x squared. And of course, negative 1 squared is constant and equal to 1, so we don't really need it. So my area formula in its best form is pi multiplied by the natural log of x squared. Moving on to the integration formula. We know that the volume is the integral from a to b of the area formula. We know a is 0. We know b is 1. And we know the area formula is pi natural log of x squared. So this problem is all finished except for the integration, which we'll do now. Remember that the 0 gives me a problem in that at 0 my function evaluates to infinity. So 0 is actually going to be my problem for the improper integral. That's going to be the problem spot, the point of discontinuity, if you will. So the integral is now the limit as a approaches 0 from the right of the integral from a to 1 pi natural log of x squared. Now we're going to figure out the antiderivative of well, let's just do natural log of x squared first, because that's going to be a little bit of a difficulty. This integral kind of gives me problems because the u substitution doesn't work. You know, if you decide that u is equal to natural log of x, du dx is 1 over x, and I don't see a 1 over x in the integrand to balance that out. So it really means that the next idea that we can do is to use an integral by parts. And this is kind of a difficult one because it doesn't really follow the Liotte rule that we did before. In this case, we're going to have to make our u equal to the natural log of x squared. which would make our dv equal to dx. The next step here is to find my du and my v. And with those two things available, now we can just go ahead and put this into our formula. Here's that integral by parts formula. There's a substitution for u. There's a substitution for v. And there's that substitution for du. Let's simplify this. And at this point, I really hope that you memorize the antiderivative for the natural log of x, because that's going to save you from doing yet another integral by parts. So to refresh your memory, the antiderivative of the natural log of x is x natural log of x minus x plus constant. So that gives me that the antiderivative of natural log of x squared is equal to x natural log of x squared minus 2x natural log of x plus 2x plus constant. So now that we have that antiderivative, we're going to substitute it into our volume formula. Let's get back to our volume formula. We knew that volume is equal to the limit as a approaches 0 from the right of the integral from a to 1 of pi natural log of x. Substituting our antiderivative here. And then next we will substitute our upper and lower limits. And isn't that a beautiful looking expression? We've got pi multiplied by 1 multiplied by the natural log of 1 squared minus 2 pi 1 natural log of 1 plus 2 pi times 1. And then we've got this limit of a approaches 0 from the right side of pi a log a squared plus 2 pi a log a plus 2a. Now the good news is there's a lot of this that actually is equal to 0 already, because we know the natural log of 1 is equal to 0. So we can make those substitutions. And we could also directly substitute into part of the second, into the limit over here in the second one. So we've got 2 pi a, substitute 0 there. And that makes things look a little bit nicer when we simplify. So now we have two limits to deal with. I'm going to separate these limits out and simplify just a little bit more. And let me tell you, neither one of those limits come easy. They are both indeterminate forms. So, keeping that in mind, let's take a look at the second one. Okay, as a goes to 0, 2 pi a will go to 0. But the natural log of a, as a approaches 0 from the right, that's actually going to go to negative infinity. Meaning I have a disguised form of L'Hopital's rule. So I'm going to get this set up for L'Hopital's rule by creating a ratio. I'll just leave that 2 pi on the outside of that limit since it's constant. And I've got the natural log of a over 1 over a. So I'm going to use L'Hopital's rule now. So I'm just left with the limit equals 0. Well, that's a relief. Let's try the other limit. Like before, I'm going to put that pi on the front of the limit. And then I'm going to analyze each one of those factors separately to start with. Now this first one, the natural log of, or the limit as a approaches 0 of a, that's easy. That's just equal to a, or 0. But the second one, natural log, as a goes to 0 from the right side, natural log of a approaches negative infinity. And when you square that, you actually approach positive infinity. So just like before, and I can hear you groaning, just like before, this is going to be an indeterminate form. So let's get set up for L'Hopital's rule. So we'll get that ratio in place. Take the derivative of the numerator and denominator. Now be careful of this numerator because this is actually going to be a power rule. So the derivative of anything squared is 2 times that anything to the first power. multiplied by the derivative of the thing inside the power. Now, doesn't that look pretty monstrous? Okay, after you've taken a minute to admire that, go ahead and simplify. And that just brings you down to negative 2 pi, the limit of a natural log of a, which, by the way, we have done already right over here. So I know that it's missing a negative, but that negative isn't really going to matter to the limit. We already know what this limit is, and it is 0. I mean, you could use L'Hopital's rule one more time if you wanted to, but I think you're kind of sick of doing that by now. And since you already know the limit, let's just make that the limit. Okay, so we've had 2 limit problems already in our rather difficult problem, I have to say. So let's just put everything together. Okay, this is where we left off. And we know that that red limit was 0. And we knew that the purple limit is 0. And that gives us a really nice answer. The volume of this infinite region is going to be 2 pi. And that completes our chapter, what is this, a chapter 9 practice test. Good luck, everyone. I know that these last 2 problems were really intense, especially that last one. And we'll see you at the next one. Good luck on your test. Have a good one.